For decades, the popular consensus has dismissed sharks as primitive automatons, simple, instinct-driven eating machines governed by a tiny, walnut-sized brain. In reality, the brain of an adult great white shark is highly complex, Y-shaped, and measures up to 2 feet long from its scent-detecting bulbs to its brainstem. This historical underestimation stems directly from the anatomical methods originally used to study them, specifically the practice of serial dissection. When morphologists physically slice a biological specimen into sections, the cutting action introduces mechanical shear. This physical distortion permanently destroys the intact three-dimensional geometric integrity of the soft tissues. Because of this spatial warping, early researchers looked at the shark's large, laterally positioned cerebral hemispheres, the centers for learning and memory, and incorrectly identified them as mere olfactory bulbs. Relying on destructive physical manipulation compromised our understanding of elasmobranch's spatial morphology and cognitive capacity for over a century. To correct these anatomical distortions, researchers have turned to modern volumetric imaging, T1-weighted MRI, and CT scanning. Scanning intact full-body specimens requires clinical machinery originally designed for human medical diagnostics. By detecting variations in how water molecules within the body respond to magnetic fields, a T1-weighted scan generates high-contrast delineations of tissue microstructure without ever making a physical cut. These intact 3D scans reveal that lamnid sharks, like the great white, mako, and salmon shark, are highly specialized, convergently evolved bioengines. By preserving the exact spatial relationships within the body, non-invasive scanning bridges the gap between a static anatomical map and the dynamic living physiology of an apex predator.
In vertebrate locomotion, muscle tissue divides roughly into 2 types: glycolytic white muscle for fast, explosive twitches, and aerobic red muscle for slow, continuous cruising. In most teleost fish, red muscle sits directly beneath the skin along the lateral line, but in lamnid sharks, this tissue is packed deep medially against the spine and shifted anteriorly toward the head. This 3D reconstruction from a mako shark MRI scan isolates those specific red muscle loins, suspended deep inside the semi-transparent mid-body. Using segmentation analysis, researchers partitioned this exact tissue volume, mapping the precise trajectory of the muscle running alongside the spine. To quantify this internal geometry, researchers measure a metric called DMV, the exact distance spanning the red muscle and the vertebral column. This axial cross-section clearly demonstrates that measurement. The marker highlights the tight anatomical clearance between the dense black vertebral column and the lighter red muscle mass. This arrangement centralizes mechanical power deep within the core of the animal, rather than along its outer edges. To understand how this core engine scales, researchers turn to the salmon shark, a cold-water relative of the temperate mako. This graph charts the relative cross-sectional area of red muscle along the body. The solid black line shows MRI data from a 9-kilogram salmon shark, indicating a red muscle endpoint extending much further posteriorly than historical dissection data, shown in dotted lines. Because this specific MRI readout contradicted established anatomical records, the research team performed a targeted physical dissection to cross-validate the scan. These side-by-side comparisons reveal the discrepancy. The MRI scan on the left registered a mass that visually matches red muscle. But the physical dissection photo on the right confirms this extended tissue is actually a massive force-transmitting structure. This structure is the hypoaxial lateral tendon, a kinetic linkage possessing an identical MRI signal intensity to the red muscle it attaches to. Looking closely at the sagittal section in panel D, the dashed yellow line marks the precise boundary. Here, the muscle tapers off entirely, giving way to the crescent-shaped origin of the tendon anchored directly within the myocepta. Solving this signal overlap mapped a complex kinetic linkage, proving that 3D imaging requires targeted physical sampling to verify structural transitions. This deep core anatomy solves a severe ecological hurdle. Salmon sharks hunt in North Pacific waters as cold as 6 degrees Celsius, yet they must maintain a regional core temperature up to 26 degrees. Thermal conductance dictates that heat moves rapidly from a warm source to a cold sink. Without deep tissue insulation, the heat generated by the cruising muscles would bleed out into the surrounding white muscle and be lost to the ocean. This graphic compares the streamlined mako on top with a thicker, cold-water salmon shark below.
Following the yellow arrows on the cross-sections measures insulation depth. The mako's red muscle sits 13.5% from the perimeter, while the salmon shark's is buried deeper at 22%. This relationship between body mass and structural proportion is known as allometric scaling. As the salmon shark grows, its morphology adapts to the cold. The peak mass of its red muscle dynamically shifts anteriorly, moving closer to the head, to optimize the centralization of heat in larger, heavier specimens. Volumetric geometry dictates a species' environmental range. The exact spatial depth of this muscle tissue allows these sharks to thrive in subarctic polar extremes. This centralized anterior engine drives a specific method of high-speed travel called thunniform locomotion. It relies on a stiff-bodied swimming node where kinetic power is isolated completely in the posterior half of the animal. Instead of flexing its entire body, the shark uses the hypoaxial lateral tendon to operate like a mechanical driveshaft, transferring kinetic energy generated deep in the core directly to the tail. Supporting this engine is the retia mirabilia, dense networks of counter-current heat exchangers bounding the arterial and venous blood supply. As metabolic heat exits the red muscle through the veins, it passes tightly alongside cold, oxygen-rich arteries coming from the gills. The heat transfers into the incoming cold blood, trapping the thermal energy inside the muscle. The temperate mako shark operates with roughly 20 rows of these lateral retia. The subarctic salmon shark, requiring extreme thermal retention, packs between 60 to 69 rows. The lamnid anatomy operates as an integrated bioengine, coupling thermodynamic efficiency with high-thrust locomotive power. This morphological optimization extends beyond the cruising muscle, governing the layout of the elasmobrand's internal organs. CT scans of shark digestive tracts have revealed precise structural fluid dynamics at work within their spiral intestines. Rather than a simple tube, the intestine forces digesta through an asymmetric unidirectional flow path, slowing the transit rate to maximize nutrient absorption. This geometry operates biologically as a Tesla belt, a fixed structure that permits fluid to flow easily in one direction, but strongly resists reverse flow without using moving parts. Piloting an organism with this level of mechanical and thermal complexity, from its high-thrust propulsion to its heat-trapping vascular beds, requires the substantial processing power of its linear, 2-foot-long brain. Volumetric data has dismantled the myth of the primitive automaton. From their neural architecture to their thermal engines, apex elasmobranchs are refined examples of engineered morphological optimization.